Okay, we're going to continue on. Got into a good chunk of chapter last time, and obviously we finished up talking about salts, or kind of left off talking about salts. And as we talked about this morning as well in lab, again, when we look at a salt, which is really just an ionic compound, what we're trying to determine is will any part of the salt actually go through hydrolysis? And that's always the question of something that could occur is the salt, because it is typically there with water as a result of a reaction of an acid and a base. The idea is, are they going to basically react with each other and go through hydrolysis? So, as we talked about, there are some rules that help us sort of decide whether or not a salt will go through hydrolysis. And again, it is that relationship that we talked about, which is uh, the relationship between really sort of either the acid and its conjugate base, are really the base and its conjugate acid sort of relationship. And as we talked about a number of times, including last time, that again, opposite relationship. If something comes from a strong acid, its conjugate partner is going to be relatively weak, which means in sort of the realm of salts, we would expect no reaction to occur with water. We would expect it to be basically a neutral salt in that case, and it would not go through hydrolysis. If it comes from a weak acid, that conjugate partner will be relatively strong, and this guy will go through hydrolysis. So again, like I wrote earlier this morning, if we had acetate, it comes from acetic acid, and acetic acid is a weak acid, which means technically speaking, because it comes from acetic acid, our acetate is going to be basically like a conjugate base. And that is how it's going to react with water. It's going to basically do the Bronsted definition of a base, which means in this case, it's going to accept the H plus. Result of that is, as we also talked about, it will always make where it comes from. And in this particular case, it will make some hydroxide. And we would expect this salt, the acetate part of the salt, to go through hydrolysis. And as a result of that, because it is producing hydroxide ions in solution that are free, we would expect the solution to become basic. Um, in addition, if we were to do some type of calculation with an ice table, which is typically what you would do in this situation, you would also want to make sure, because we got some hydroxide happening here, you would want to make sure again that you are using the Kb value. As I mentioned last time, these are typically the problems, definitely salt type problems, are typically the problems where you will be given sort of the wrong K value to do the calculation with. So again, in a problem, if you were given a problem like this, you most likely would be given the Ka value for acetic acid, and not anything to do with acetate, but just the Ka value for acetic acid. So again, that is where our Kw would come into play. We could use Ka times Kb, and we could use that to figure out the appropriate Kb value. And obviously, as we use this morning and a bunch of times here, 1 times 10 to the minus 14, again, is the value that we would associate with that. Same sort of relationship when we look at a base and its conjugate acid. Again, if it is a strong base, its conjugate acid will be relatively weak. And once again, in terms of salts, that means we would expect the solution to be neutral. That is essentially why they say group 1 and group 2 on the periodic table are neutral salts. And that's because, again, group 1 and group 2 on the periodic table is essentially where a lot of our strong bases come from, things like sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth. So probably that part of the salt, like a sodium, a potassium, or something like that, would have originated from a strong base, and again, would not go through hydrolysis really because of that. So remember, group 1 or group 2 pretty much will not go through hydrolysis. If it's a weak base, its conjugate acid will be relatively strong and will go through hydrolysis. And the difference here is we're just going to get a different sort of outcome. So as we saw this morning, again, if we had NH4 plus, which most likely came from ammonia, which is a weak base, this would then be like its conjugate acid. And once again, that is how it's going to react when it reacts with water. It's going to react as an acid and actually send the H plus over to the water. The result of that, again, you will make where it comes from. And in this particular case, we'll make H3O plus, which again, because it's generating H3O plus in solution, is going to make that solution acidic because we now have more H plus ions basically float around freely in that solution. And same idea if you needed a pH or something like that, it's a nice table sort of calculation. But once again, you do have to be careful because you most likely will have the Kb value for NH3 in this problem. And again, you will need to use something like Kw, obviously, to switch it over to the proper one. So very commonly in these type of problems with salts, you're typically sort of given the wrong K value in the problem, and you guys kind of switch it. And obviously, if it's anything that comes from strong, it's basically going to be a neutral pH of 7 in this case, if it is something from a strong acid or base. Any questions on that there? All right, so I don't think we did any examples. So let's take a look at some examples here. What is the pH of a 0.45 molar KCl solution? So take a few moments there and think about it. Okay, so let's take a look at this one here. So we do have a salt, which again, as we've been talking about, is really just an ionic compound. And typically salts will 100% break apart into ions. So in this case, we got a K plus and a Cl minus. And as I mentioned before, what we want to think about is whether or not any part of the salt will go through hydrolysis. By the way, we also talked about, I think at the very end last time, that it is possible that both parts of the salt does go through hydrolysis. So that is also a possibility as well. In this particular case, if we look at K plus, that is group 1 on the periodic table, most likely came from something like potassium hydroxide, which means not going to go through hydrolysis. Again, going to be really a neutral salt. Cl minus most likely came from hydrochloric acid, is most likely the originator of the Cl minus. And hydrochloric acid is a strong acid, which means its partner there is going to be relatively weak. And that means it will not go through hydrolysis either. And that means in this case, no calculation actually needed. The pH should be 7 in this case, again, because neither part of the salt in this case will react with water, and we would expect it to be neutral. Questions on that? All right, let's take a look at one where you probably do need to do a calculation. Excuse me. Consider 0.3 molar sodium fluoride. The Ka for HF is 7.2 times 10 to the minus 4. What is the pH? So you do need an ice table. Okay, let's take a look. So again, we're given a salt here. So we want to again kind of analyze both parts of the salt and see if we got anything that's going to go through hydrolysis. So that's going to give us a sodium and a fluoride in this case. So we've obviously talked about sodium a good amount, so we don't really have to worry about the sodium. Again, it's group 1 on the periodic table, most likely came from like sodium hydroxide, not going to go through hydrolysis. Now our F minus in this particular case will go through hydrolysis, and I know that because it does come from a weak acid. And again, as I mentioned before, there's sometimes a lot of information in these problems, including the fact that I do see HF here and a Ka value for it, which makes me know that this is a weak acid. And that means that this would be its conjugate base. And this guy would go through hydrolysis again because it comes from something that is weak. So here it is, the F minus part of it that will go through hydrolysis. And that's really the reaction that we want to write. So in this case, F minus will react with water. The good news on this one is, frankly, it doesn't have an H to give, so it should do what it's supposed to do, which is act as a base in this case, and it should accept the H plus. Once again, it always makes where it comes from, which in this case is hydrofluoric acid, which is a weak acid, and it will make hydroxide in this case. First off, any questions on that reaction there? Now, here we're going to do a ice table, and we'll start with the initial concentration F minus, which is 0.3 molar. I know that because when I look here, it is a 1-to-1 relationship between those two. And that means that this guy's concentration is also 0.3 molar. We're going to do zeros for our other here. Change going to be minus x plus x plus x. At equilibrium here, we should end up with 0.3 minus x, x, and x. Any questions on the ice table here? This is going to go into my K expression here, which would be my HF, my OH minus, and that's going to be divided by my F minus. By the way, this is a K, A, B, C, D, E, F, G. Not everybody at once. Thank you. What do I see over here? I see hydroxide, right? Which tells me before I even do the calculation, my answer should be basic, right? And because it's hydroxide, I should be using a KB. So again, super important. Most people will roll with, once again, the wrong value given to you, which is the Ka value in this case. So again, these are very common problems where you are sort of maybe enticed there by the wrong K value that's given to you in the problem. So we do need to convert our Ka value that's given to us to a Kb value. And again, we'll use Kw to do that. So in this case, our Kb will be our 1 times 10 to the minus 14, which is our Kw, obviously, divided by our Ka value that was given to us, 7.2 times 10 to the minus 4. And that's going to get us here. Call it 1.4 times 10 to the minus 11. So again, really important that you are using the right value. Writing the equation is really important for that, so it sets everything up. By the way, again, sometimes people really struggle sometimes with the equation part of it. But if you kind of think about it, you almost have all of the equation that you need. You should know the salt should always react with water. And if you just look in the problem, they'll actually tell you kind of, what you're going to make in this case. So all you have to figure out is should it be OH minus or H3O plus there at the end. Put in our values here. We're going to go a little x squared divided by 0.3 minus x equals, again, our KB value in this case. That is a small kb value, so I'm going to assume x is equal to 0. So that's going to reduce that down to x squared 0.3 equals 1.4 times 10 to the minus 11. We're going to multiply followed by a square root. Yeah. So if we do that, we'll take that times 0.3, a little square root action. And I get a lot of zeros. X is equal to 2.04 times 10. I don't know, 1, 2, 3, 4, 5, 6, minus 6, I think. It is an assumption, so we do want to check. So just like a normal check, we're going to divide it by our initial 0.3 and times it by 100%. And I think we should be okay in this case here. We're not even 0.1%, so the check is good in this case. That does mean second very common mistake people make is they do not realize that the X in this case is not the H plus concentration. Again, it is the OH minus concentration. So here the OH minus concentration will equal our X value. That means that we can get our POH from that. And that's going to get here minus the log. Probably should use the right number here would be helpful. Probably, maybe. 5.69. And again here, if by some chance you did this and you thought that was the pH, it really shouldn't make sense to you because it should be a basic pH. So here to get to our pH, we're going to do 14 minus that. And that should get us to 8.31, which is a basic pH. And again, what we would expect in this case. Any questions on any part of that there? Yeah. For the pOH? Yeah, so negative log and then the number. Yeah, so if you have a display calculator, negative button, log button, and then 2.04 exponent button, negative button, and 6. Yeah. Again, if you have a non-display, you gotta go backwards, like we talked about previously in this chapter. Yeah. Other questions? All right, let's take a look at another one here. Maybe. Let's take a look at that one if we don't see it gets changed. Maybe. Come on. Come on. There we go. Jeez. Maybe. All right. What is the pH of this solution here? 0.75 molar sodium cyanide. And if we break that salt up, it's going to make a sodium ion and a cyanide ion. And as we talked a lot about up to this point, obviously, again, we're not going to be concerned about the sodium here from group 1. But the cyanide here, we should be concerned about because I, again, do see a Ka value for HCN, which seems like the weak acid that most likely came from. And that means that this would be its conjugate base. And we'll go through hydrolysis in this case. So again, starting with our CN minus and our water. Once again, because it comes from a weak acid, it's going to act as a base. And logic tells us it doesn't have an H to give. So the only possible thing it could do is accept the H, obviously, in this case. Once again, we'll always form where it came from. So you kind of have that as well here. And when the water loses the H plus, it's going to make hydroxide. So once again, here we should know before we even do the calculation that we should end up with a basic pH when it's all said and done, because we again are producing hydroxide in this case. Going for our ice table here, our initial concentration going to be 0.75. Once again, it's a 1-to-1 relationship between those. So it's the same concentration. 0, 0, minus X, plus X, plus X. That means at equilibrium. 0.75 minus X, X, and X. Any questions on the table here? This again is going to go into our KB, and I know once again I should be using a KB because again, do you see hydroxide on the right-hand side of the arrow? If I were to have seen H3O plus, then I should be using a Ka value. So again, the importance of being able to write these equations correctly can help you with the calculation part, again, based on what you see on the product side. So this is going to be our products over our reactants here. A little HCN, a little hydroxide, and CN minus. Obviously, here we do need to calculate our KB. So just like we did on the previous problem there, 1 times 10 to the minus 14 divided by our Ka value here, 6.2 times 10 to the minus 10. Going to yield us a KB of 1.6 times 10. Looks like 1, 2, 3, 4, 5 minus 5 here. So that's going to be 1.6 times 10 to the minus 5. And now we're good to go. We can put our equilibrium into here. So x squared divided by 0.75 minus x equals 1.6 times 10 to the minus 5. Again, we could assume x is equal to 0. That will get us x squared 0.75, 1.6 times 10 to the minus 5 it equals. Multiplying followed by a square root again. Going to 1.6 there to the minus 5 times 0.75 and a little square root action here. Going to get us here an x value of 0.00348. We do want to check it, so we'll divide it by 0.75 and times it by 100. Got like 0.4%, so the check here is good. Once again, looking at our ice table, we need to remember that in this situation, this again equals the OH minus concentration. So again, the OH minus concentration equals our X value of 0.00348, giving us a POH minus the log of it. And that's going to get us here minus the log 0.00348, 246 on the POH. And obviously here the pH would be just 14 minus that. And that's going to get us an 1154 pH, which is definitely basic and, again, what we would expect in this case. Any questions on it? So in this case, we have two that did go through hydrolysis, did produce hydroxide, which again is typical if the salt does come from a weak acid. If you had a salt, again, that came from a weak base, I would also go through hydroxide. The only difference is it will produce H3O plus, so when you do solve for X in that situation, that could go right into the pH equation at that point. Yeah. Any questions on salts and calculations here? Okay. See here. Yep, through this page there, I think. There we go. We also again talked about aluminum this morning and last time, and again, a lot of metals, especially transition metals that plus twos, plus threes, can also act as a salt and go through hydrolysis. They will go through an acidic process where one of these sort of hydrogens is lost to another water. That is what produces H3O plus, and again, that is what makes it acidic. We touched upon this last time, but just to reiterate, again, if you happen to have a salt where both parts can go through hydrolysis, you would compare the Ka value to the Kb value. And again, I think the one that we looked at the very end there was NH4NO2. Again, this is NH4 plus, which definitely will go through hydrolysis, again, because it comes from ammonia, which is a weak base. NO2 minus would also go through hydrolysis as it comes from nitrous acid, which is a weak acid. So again, in this particular case, we compare the Ka to the Kb, and whichever one's larger is what we would expect to occur. So if the Kb is larger for the anion, then we would expect the basic reaction to occur. If the Ka is larger, the acidic reaction, and obviously a more neutral sort of situation if they are approximately equal to each other, the Ka and the Kb value. And this is just a table that sort of summarizes a lot of the salt stuff that we talked about. Again, neutral salts, acidic, basic salts, and again, possibly could go through both situations. So we're actually going to go backwards first before we go forward because we did skip over a few things last time. So I did want to go back and sort of talk about that there. And I think this is where we kind of did that. All right. So that we talked about. All right. So I just want to talk a little bit about acid strength and how we determine acid strength or maybe compare acids in terms of their strength. And when we're comparing acids in terms of strength, it does depend on the type of acid that you're sort of looking at. So there's really kind of two types of acids that we come across. There are acids that do not have oxygen in them, and there are acids that do have oxygen in them, and they're sometimes referred to as oxyacids because they do contain oxygen. So when we look at an acid like this, like HF, HCl, all your group 7 there, HBr, HI, When we look at acids like this, where again they each do not have oxygen, one of the things you may think is sort of important in terms of what makes something a stronger acid versus a weaker acid is maybe something like electronegativity. And the idea of electronegativity here with these type of acids is actually not what you look at. And the idea here is with these acids is the overwhelming property that we look at is really the ability of the acid to release those hydrogens, right? And that's what makes something a strong acid, say, versus a weak acid. A strong acid has a pretty easy time just releasing that hydrogen. A weaker acid is going to kind of hang on to it, not going to want to release it as much. And when we look at this type of acid, although you may think electronegativity may play a role in it, it actually doesn't. And the major thing that we look at is what is known as bond enthalpy or bond energy. And that is the energy required to break that bond between the hydrogen and whatever it's attached to. So when we look at bond enthalpy, we see that it actually increases as we go up, say, group 7. And that means when we go in this direction in group 7, it takes a lot more energy to break this bond than it does, say, this bond. And that is why HF in this case is actually a weak acid because it takes a lot more energy to break that bond between the hydrogen and the fluorine, which means less of that is going to come off of the H plus. Takes less energy to break this bond, which means you're going to get a lot more of the H plus come off in that situation. And that's going to actually make it a stronger acid. So in comparison of HCl to HF, HCl is a stronger acid than HF because it takes a lot more energy, almost 130 kilojoules more of energy to break that bond between the hydrogen and fluorine as it does between the hydrogen and fluorine. In fact, the strongest acid in that group 7 is actually hydroiodic acid is actually the strongest acid. And that's because it has the weakest bond energy, which means when you go to break the HI bond, it doesn't take a lot of effort to do so. And it's going to allow him to release a lot more H plus into solution. So in group 7, what we look at in terms of sort of acid strength when comparing is actually bond enthalpy. And acid strength actually increases as you go down group 7 for those acids that are there. And that means that hydrofluoric acid is the weakest acid of the bunch. Hydroiodic acid is actually the strongest acid. That's why these three are on our list of 6 strong acids, because again, the hydrogens can come off a lot easier than it does going the other way. And that is opposite of the electronegativity trend, which increases as you go up the group, right? So in this case, we look at bond enthalpy. Now, and you could also see that from this slide from your book as well. Again, increasing acid strength going down and to the right. When we look at a acid that contains oxygen, which is a oxyacid, most of those oxyacids will have this bond. And this bond right here, which is the OH bond, is a polar bond, as you may remember from bonding, where the oxygen is more negatively charged, right? And the hydrogen is more positively charged because of the difference in electronegativity, right? And when we have an oxyacid, there's really one of two things that we look at in terms of comparison of acid strength. We may look at the electronegativity of the center atom, or we may look at the oxidation number or oxidation state of that central atom. So let's take a look at in what situation should we look at what. And let's just say we were going to compare these two acids here. So we got a little chloric acid, I think, bromic acid in this case. And in this particular case, pretty much everything on the outside is the same. The major difference here is our central atom in this case. Now, remember the two things that we sort of look at in terms of acids that have oxygen is electronegativity or oxidation number. And if we were to assign oxidation numbers to everybody here, which you may be familiar with, or if not, we will talk about it more a little bit later on. But the easy thing to remember for now is oxygen is -2 in terms of its oxidation number, -2, -2, and hydrogen is +1 in this case. Now, when you add up all the oxidation numbers, it does need to equal the charge of the thing. In this case, the charge is neutral. So if I add up all those oxidation numbers I got going on now, that's 2, 4, -6, and +1 is -5. That means the bromine here is rolling with a +5 oxidation state in this particular case. If we were to look at over here, the chlorine, -2 for the oxygen, -2, -2, and +1. Same idea, -6 and +1 is -5. That means the chlorine is rolling with a +5. A reminder, we'll talk about it in a later chapter, but just in case you don't remember, maybe from Chem 50, or maybe you didn't talk too much about it, oxidation numbers or oxidation states are different than the charge we associate with certain elements when they're in an ionic compound. And that is because in an ionic compound, they have transferred their electrons and they end up with full electrons being transferred. Oxidation state or number is the charge these guys would have if all the electrons were sort of transferred. And the difference between an ionic compound and this compound is everybody here is sharing electrons. So what happens when they're sharing electrons, especially when they're sharing electrons perhaps with a more electronegative atom, is all the electrons are going to head outwards towards those oxygens. And that's going to make the bromine become more and more positive in that situation and more electron deficient. So things that we normally associate with negatively charged and ionic compounds like bromine and chlorine can have a positive oxidation state in a covalently bonded situation where they're sharing electrons with elements with different electronegativities. So just keep that in mind. Sometimes people are like, is it always -1 for those guys? And again, in an ionic compound it is, but in a covalent situation, they can take on a positive sort of charge. So the idea here is if we were to try to compare these acids based on oxidation number, they both are +5. So that's not going to really do us much good in this situation. So because we really can't use oxidation number or charge or oxidation state here to compare, we then default then to electronegativity. And we would want to compare, in this case, the electronegativity of these central atoms. And they are both from group 7, and electronegativity increases, right, as you go upwards in group 7. So what does that mean? That means in this particular case, if we look at each of these, what's going to happen in this situation is, I'll use red. We already have sort of the electrons heading in this direction because of the OH bond being polar and oxygen being more electronegative than hydrogen. So it's going to bring the electrons in. That is going to weaken this bond, making this more positive, this more negative, partially positive, partially negative. Now with chlorine here, because it's more electronegative, it's going to also suck those electrons in even further because it's going to also want to kind of bring electrons towards itself. And the result of that is it's going to continue to weaken this bond to a point where this is going to be able to pop off easier than in this situation where bromine is less electronegative. So even though the electrons are heading in this direction, those electrons aren't going to feel the as strong of a pull towards the bromine versus the chlorine. And it is still going to weaken this bond, but not to the same extent as this bond is going to be weakened. Bless you. And because of that, we would expect here our guy with the chlorine to be the stronger acid of the two based on electronegativity. So if we had to rank these two, because Cl is more electronegative than bromine, and that has to be the sort of our deciding factor since we cannot use oxidation state. we would expect HClO3 to be a stronger acid than HBrO3. Any questions on that? Now, when should we use oxidation number? Well, kind of in the same idea. When we look at the central atom for all of these acids, the central atom is all chlorine, which obviously means every single one of those are going to have the same electronegativity value, which means we cannot use electronegativity in this case to help us decide which one is the stronger acid. In this case, we would actually need to look at oxidation number. And here we would look at oxidation number. And once again, -2 for the oxygen, +1 means that the chlorine here is rolling with a +1. -2 for each oxygen and +1. That's -4 and +1 is -3. Chlorine +3 in this case. This is the one we just did on the previous example. +5. And over here, -2, -2, -2, and -2, and +1. That is a -7 overall, giving our chlorine here a +7 oxidation state in that case. You can also see as you put more oxygen on there, it's sucking the electrons away from the chlorine in this situation and making it more and more positive. And that's why the oxidation number increases as you kind of go around there. What that means in this particular case is kind of the same idea. Because there is a much greater positive charge here and the electrons are heading in this direction, opposite attraction, right? So it's going to be more attracted to that greater positive charge on the chlorine with the +7. And again, that's going to weaken this bond a lot more than it is in this situation where it's not going to feel as much of a pull to the chlorine with a +1 oxidation state. So in terms of acid strength, increases with oxidation number, strongest acid, next strongest, and weakest acid out of all of them is going in that direction. So our perchloric acid is the strongest, down to our hypochlorous acid is the weakest in this case. So strongest, weakest, yeah. Any questions on that? So if you have an oxy acid and you cannot use oxidation number to distinguish, you want to use electronegativity, and vice versa. If you can't use electronegativity to distinguish, then you want to look at oxidation number. Any questions on that there? All right, so I just want to touch upon that there. Now we'll go forward. Okay, next thing I'm just talk about just kind of briefly is again oxides of some of these elements. And oxides are really elements that obviously have oxygen in them, and they're kind of in a lot of cases one step away from either making an acid or a base, basically. So if you think about a lot of these guys over here, group 1 and group 2, again, if you add a little bit of water or something like that, you're going to make some sodium hydroxide, potassium hydroxide. And these are what are sometimes referred to as basic oxides because they're basically one step away from becoming a base. Over here are nonmetals together are kind of one step away from becoming an acid. So for example, if you take carbon dioxide and add some water, you're going to get yourself some carbonic acid, yeah, which obviously is an acid. If you do a little N2O5 with a couple of waters or so, you'll make some nitric acid and stuff like that. So a lot of nonmetals with oxygen will be our acidic oxides. And we do have some amphoteric oxides that can go both ways. So beryllium, our normal sort of guys over here, aluminum and so forth. These guys, again, can go either way, either make an acid or a base, depending on how they react with water. Now, we've talked about a couple of definitions of an acid. We talked about the Uranus definition of an acid, which again is something that has the ability to produce H plus or H3O plus ions in solution. We talked about our Bronsted definition of an acid is something that can donate an H plus. So we cannot forget our good friend Lewis, because he wanted an acid as well. So when we think about Lewis, we think about Lewis structures, perhaps, Jess? And when we draw Lewis structures, those usually involve what things? What are all the little dots you put on them? Those are all electrons. So maybe not surprising, Lewis definition of an acid involves electrons. And a Lewis acid is a substance that will accept a pair of electrons. So a Lewis acid is something that will accept a pair of electrons, while a Lewis base is something that will donate a pair of electrons. So when we're talking about a Lewis acid and a Lewis base, we're talking about electrons being donated and accepted. What are good things that can accept electrons? They are things that are frankly electron deficient. And what things are normally electron deficient? I don't know, maybe like a metal that has a positive charge, right? Because the only way you become positively charged is to lose electrons, which means you have less electrons than you started with. Hence the earlier conversation where we had our like aluminum that is attached to a bunch of waters around it, right? In our little guy that we had earlier. And that is because aluminum here is electron deficient as it has a +3 charge. And what is a good thing that can act as a Lewis base? Things that have a negative charge is oftentimes good Lewis bases, because usually if you have a negative charge, you gain some electrons, which means perhaps you have electrons to give. And things that are polar that have non-bonding electrons, like our friend water, is a really good Lewis base. Water, which obviously is polar, it's got those non-bonding electrons it could donate. That is why oxygen attaches to the aluminum there. Our friend ammonia, also a really good Lewis base, also polar, has some non-bonding electrons. So good Lewis bases are things that have non-bonding electrons, typically are polar, are things that are negatively charged, are also very good Lewis bases as well. Like chloride is a good Lewis base as well. It has a -1 charge and extra electrons. So you could apply Lewis acid base definition to acids and bases. So here our hydroxide, which is negatively charged, has some electrons going to send its electrons over, which means that is a base and our H plus is missing electrons. So it's going to accept it, which means that this is our acid. We could also look at something like here. Ammonia has electrons, going to send it over, acting as a base, and H plus also missing electrons, acting as an acid. Now, in this particular case, you could still use the Bronsted-Lowry definition, and in the Bronsted-Lowry definition, the H plus is going to go this way, right? Which makes it an acid, and that's going to accept the H plus, makes it a base. You end up with the same result as what's the acid and what's the base, regardless of which definition you choose. Same thing here, the H plus would go this way, which would make that the Bronsted acid because it's donating the H plus. The NH3 is accepting the H plus, which would make it the base. So the Bronsted-Lowry definition, which is talking about protons being accepted and donated, and the Lewis acid and base definition was talking about electrons being accepted or donated. They both end up with the same result of what's the acid and what's the base, but they are looking at different things. One looking at electrons, one looking at protons. Now, why would you want just to use a Lewis acid definition versus a Bronsted-Lowry definition? It actually is a much more generic way of looking at acid and bases. Here we have boron, which is a exception to the octet rule. It's an incomplete octet, which means it's definitely electron deficient and a good candidate to be a Lewis acid because it's going to be more than happy to accept those electrons from our NH3, which is going to donate those electrons and be our Lewis base. And in this situation, we have now just applied sort of a acid-base definition to something that doesn't involve a proton being transferred, right? So there is no Bronsted-Lowry definition here, but we could still apply sort of a Lewis acid-base definition here. We will definitely see Lewis acids and bases in later chapters, especially the chapter that involves complex ions. Complex ions are essentially Lewis acid and base situations that are occurring. A complex ion is similar to what we saw earlier with the water and aluminum example. We again can apply sort of a Bronsted-Lowry Lewis acid-base definition to this, and this is basically a complex ion that is formed as a result of this. Any questions on that? And again, like I said, we definitely will see that coming up. All right, so the next thing we're going to talk about here to finish up sort of part 1 of chapter 14 is diprotic acids or polyprotic acids and what we do with these in terms of calculations. And polyprotic acids or diprotic acids are really acids that have more than one hydrogen that can come off. And obviously here, something like HCl is a monoprotic acid. It has one hydrogen that will come off. Something like sulfuric acid is a diprotic acid. It has two hydrogens that will come off. And something like phosphoric acid is a triprotic acid. It has three hydrogens that will come off. As we talked about earlier today and previously as well, again, each of these hydrogens do not come off altogether, especially when you have diprotic or polyprotic acid. Each hydrogen will come off one at a time. And for every hydrogen that comes off one at a time, you will have a K value associated with that. So if we take a look at phosphoric acid, the very first thing that will happen with phosphoric acid is it will lose one hydrogen as it starts to dissociate and will form H2PO4 minus. That is when you look at a table, what is sometimes referred to as the Ka1 value here in the table. And in this case, as you can see here, Ka1, 7.5 times 10 to the minus 3. Then what happens is that one that has lost one hydrogen will then dissociate and remove a second hydrogen and will form HPO4 2 minus. And that also has a equilibrium constant associated with it, which is known as the Ka2 value, which from this table looks like 6.2 times 10 to the minus 8. The last step along the way will be HPO4 2 minus, which has already lost two hydrogens, will lose its very last hydrogen in this case, and we'll make some phosphate here. And that is our Ka3 value. And in this case of phosphoric acid, I think that's minus 13. 4.8 times 10 to the minus 13. So this is, again, a stepwise fashion that occurs. And each of these are an equilibrium that occurs as each of the hydrogens come off. Would you expect the first hydrogen to be easier to be removed than the second, or should the second be easier than the first? Which one should come off the easiest? The first one should actually come off the easiest. If you think about it, it's neutral. So as you remove that H plus, you now make something that's kind of negative, right? Which means it's going to try to hold on to those H pluses a little bit harder. And it gets harder to remove the next hydrogen and even harder to remove the third hydrogen. In reality, you're probably not going to get all that much coming off of the third hydrogen. We actually see that when we look at the Ka values for Ka1, Ka2, and Ka3. What happens to the Ka values as I continue to remove hydrogens? Do the Ka values get larger or smaller? They get smaller. And when we have a smaller K value, that means we have more reactants or products. That is a 50-50 shot. You can only be wrong once unless you guess twice the same answer. we have more reactants, right? When we have a small K value. So the K value decreases as you go down. And what that means is because we now have smaller K values, we have more of the whole acid still staying together rather than it breaking apart. So less H plus is going to come off each time as you go through that. A majority of it, as you can see here, is going to be much easier to remove that first hydrogen than the last one. Any questions on that? And that's the pattern you see with diprotic acids as well. As you go from here to here, you start to see again the K values get smaller and smaller because it gets harder and harder to remove that. Where down here, you got like a -2 charge hanging on to everything. So again, it's going to be a little bit harder to remove that along the way. By the way, as we talked about, typically on the K values, right, for weak acids, as we might have mentioned before, this is typically what you see for sulfuric acid, which is a strong acid. You typically, again, see it's like it's a large value, which is not obviously helpful for calculations. The reason it's on the table is not really for sulfuric acid. It is for what you get after you remove that first one, which is bisulfate there or hydrogen sulfate, and that is a weak acid, which is the Ka value that you see right there next to it. Now, again, it does come off in a stepwise fashion. In the earlier class, you might have just thought they all drop off because, again, in the earlier class, maybe like Chem 50, you maybe were just looking at the overall reaction. So if we were to add all these together, what would happen is this and this would cancel, this and this would cancel, and you're left with H3PO4 goes to 1, 2, 3 hydrogens and a phosphate. And so probably most of the time up until this point, you probably just looked at the overall reaction of what's happening, where it kind of appears that all three of them just pop off at one at a time, are all at once, all three of them, but they do pop off again one at a time in this case. Any questions on that? How does polyprotic acids affect calculations that we're going to do? So let us do one here and see what we end up with, maybe. Maybe. We'll come back to this here real quick. All right, so we're going to do this problem here together and see what we should be thinking about if we have to do a calculation of a polyprotic acid. So we are going to take phosphoric acid there, and we have our three Ka values. Again, as we just saw, there's one for each of the hydrogens to come off. And in this particular problem, we want to know everything, basically what everybody's concentration is all the way along the process, and also what the pH is. So we're going to start with 5 molar of phosphoric acid. And we're interested, like I said, in this particular problem, pretty much what everybody's concentration is, and also that pH. So let's start with the first step that's going to happen, which obviously is our phosphoric acid here is going to lose one hydrogen, right? And it will make our H2PO4. And as we just saw on the previous slide there, this is our Ka1 value here that we can look up in the table. So to do this, we're going to do an ice table. So we will start with our 5 molar here. We're going to go 0 and 0. Change is going to be minus X plus X plus X. And we're going to end up with 5 minus X, X, and X. Any questions so far on the table? This is going to go into our Ka1 expression. So our Ka1 expression, again, is our products over our reactants. And that basically is going to give us X squared divided by 5 minus X equals our Ka1 value of 7.5 times 10 to the minus 3. We can assume that X is equal to 0 in this case and give it a go. And that's going to give us X squared divided by 5 is equal to 7.5 times 10 to the minus 3. Like normal, we're going to multiply and then square root it. And if we do that, 7.5 to the minus 3 times 5, a little square root action. And we're going to end up with here an x value of 0.194. We did make an assumption, so definitely we want to check it. We're going to take 0.194, we're going to divide it by 5, times it by 100%, and hope for the best. And it is a good situation in this case because I changed the number years ago and I didn't want to do another quadratic. Uh, this was like 3, like I think it was originally. We were in trouble. We did quadratic unit. Here, that's good. So what that means in this case is a couple things. Off this very first dissociation, we have a lot of answers to what we're looking for. So we know our x value is this guy. So right off the bat here, we know the concentration of H2PO4 minus at equilibrium is 0.194 molar. We also can see that that is our H plus concentration as well. So we have the H plus concentration at equilibrium, 0.194 molar. And we also have this guy's at equilibrium, our phosphoric acid concentration at equilibrium is going to be 5 minus, come here, 5 minus our x value, which is 0.194. Going to give us a 4.806 molar. So right off of our first ice table, we got this answer. We got this answer. And we actually have this answer as well. So that ain't too bad in this case. Any questions so far? Now, unfortunately, they want a bunch of other things. So the only way we could really get to this guy is we have to do the next hydrogen coming off, basically. So we have to do our second hydrogen coming off in this case. So the next step that's going to happen is our H2PO4 minus is going to lose that second hydrogen and make HPO4 2 minus, which again is something that we're looking for. And in this particular case, that is our Ka2 action that is happening here, as that is the second hydrogen that's coming off. And our Ka2 there, should have looked at it, 6.2 to the minus 8. So this is our Ka2, 6.2 times 10 to the minus 8. All right, so just like previously, we're going to do an ice table. So initially, do I have any of that in the solution to start with? The answer is I do, and it is right here, right? After the first hydrogen comes out, I do have some of that floating around in the solution. And that means the concentration I'm starting with is my equilibrium concentration here for my first table, which is 0.194. So 0.194. How about hydrogens? Or any hydrogen from that first table there? There is as well, right? So we actually do have some hydrogen that came off of that first hydrogen into the solution. Also a concentration at this point of 0.194 as well. So a little bit different on this table. We actually do have some starting amounts on both sides of the arrow in this case. We don't have any of this, as that's sort of what we're looking for in this step of the game. The rest of the table is going to be similar. It's going to be minus x. This is going to be plus x and plus x. This is going to give me 0.194 minus x, 0.194. Don't forget this is a plus x on this side, and that is an x. Any questions on that table? So here we're using our equilibrium values for our initial values of our next sort of step as they're coming off. This is going to go into our Ka2 expression of H plus, HPO4 2 minus, and our H2PO4 minus. And that's going to give us here 0.194 plus x times x divided by 0.194 minus x equals 6.2 times 10 to the minus 8. I'm doing great with the assumptions, so why not continue? I'm going to assume x is equal to 6. No, it's equal to 0 in that case. And that's going to give me now 0.194 times x divided by 0.194 equals 6.2 times 10 to the minus 8. I think I could do it. That's going to cancel out. And that's going to give me an x value of 6.2 times 10 to the minus 8 in this case. Questions on that? We do need to check it because, again, we did an assumption. So we could take this and divide it by 0.194 times it by 100. I think we should be fairly good at this point. Minus 8 divided by 0.194 times 100. It's not even 0.1%. So the check here is good. Yeah. So off of this second table, we're now able to figure out our concentration of this guy, which is one of the ones we're looking for. So in this particular case, our concentration of HPO42 minus at equilibrium will equal 6.2 times 10 to the minus 8 molar in this case. Yeah. Question on that. Yeah. No, it's a thing where either you're subtracting or adding from a number. So it's the change part is basically what we're removing it. Again, you could do it for anything that's positive, anything that's negative. You just can't do it from this one because it started at 0. And if you started at 0, even if you made a super small amount, that's more than you started with, right? It's significant. Plus, just mathematically, you have nothing to solve for if you get rid of all the x's, so you got to keep one there. But you can, when we do the assumption, is anything you're going to subtract an x from or add an x to is the x's you can get rid of. Yeah. Other questions? Now, that takes care of this guy, right? But let's just stop for a moment here and take a look at these guys' concentrations at this point. If I take my x value and I put it back into here and here, do those concentrations change really? All right, put it in your calculator and see if they change. Super slight, right? They're basically still going to be, if you had to give me the concentration, still going to be 0.194, right? It's going to change very slightly, right? But it's not going to significantly change. It's still going to be basically 0.194 if you put that number back into your calculator. So a very slight change happening with those, but overall concentration is still remaining pretty much the same at this point, unless you go like 6 decimal places to the right and look at how far out that is. All right, so we got that. So the last thing that we're kind of looking for is the phosphate. And unfortunately, the only way to get the phosphate is to lose all 3 hydrogens, which means we have to get all the way down to this step. So let's take a look at that. And that will require our third one there. And that's going to be HPO42 minus is now going to lose its third hydrogen. And that is going to bring us to our Ka3 value of, I'm getting old, 4.8 to the minus 13 sounds exactly what I did not remember. 4.8 times 10 to the minus 13. All right, so same idea here. When we come to our initial at this point, we definitely still have now some of that formed, right, from the result of the previous spot. So we're going to use our equilibrium concentration from the previous step as our initial, so 6.2 times 10 to the minus 8. How about hydrogen? Do we still have hydrogen? We do over here. And as you put your number in, pretty much still staying at 0.194 in this case. So we have 0.194 and we got nothing going on there. Change going to be minus x plus x plus x. That's going to be 6.2 times 10 to the minus 8 minus x, 0.194 plus x and x. Going into our Ka3 expression, again, products over reactants. And that's going to give us 0.194 plus x, x divided by 6.2 times 10 to the minus 8 minus x, going to equal our 4.8 times 10 to the minus 13. Why not? We're going to assume for our third and final time, x is equal to 0. Again, getting rid of only the x's we're adding or subtracting from a number. And now we can solve this by obviously multiplying that to that side, followed by dividing that, right? So if we do that there, we're going to go 4.8 to the minus 13 times 6.2 to the minus 8 divided by 0.194. That's going to give us an x value of 1.5 times 10 to the minus 19. Once again, we could check it by dividing by whichever one you like. I'll take the bigger number. And the check here is good. Again, we're not even near 0.1%. So what does that give us? That does give us our concentration of phosphate at equilibrium, which is 1.5 times 10 to the minus 19. What happens to the H plus concentration, the HPO42 minus concentration? Does it significantly change? Again, if you put your X value in there, not much is going to change, and that unless you go thousands of decimal places to the right, basically remains the same. So that means at this point, we have now calculated our last thing, except for the pH. So let's talk about what we need for the pH, which is obviously the pH is equal to minus the log of the H plus. What we see here when we look at the calculation is this, the concentration of H plus that came off originally. Not that, when we circle the right one there, right there, same number. 0.194 molar, right? How much H plus came off on the second move, if I ever get it to turn? The amount of H plus that came off is that. Yeah, that's basically new amount of change, right? So we got off in the first one, 0.194 molar. In the second one, we got a whopping 6.2 times 10 to the minus 8 molar of H plus to come off. Not all that much, right? A lot less. What happened when we popped off the third one? We got off even less, basically, right? 1.5 times 10 to the minus 19. So that shows you, as we were talking about, it gets progressively harder, right? To remove those hydrogens. Not much is coming off. The majority of all the hydrogens that came off when? The very first step, which means this is the situation that usually occurs for most polyprotic acids, which is if you have a question where you just need to calculate the pH, it's probably very safe to just do the first table and use the H plus concentration from there, as not much is going to probably come off in subsequent steps. And you wouldn't have to go all the way through it. The reason you have to go all the way through it and what we just did is we needed the concentration of everything, right? So the only way to get the phosphates go all the way to the last step. So that's why you had to go through it. But if you came across a question, you just needed the pH, do that first ice table, and you most likely will be in good shape. So we'll finish it out here by getting the pH. And that's going to get us 0.194, a pH of 0.71. Definitely acidic in this case. Guess what happens when you change the number? Yes, to make up things. Any questions on polyprotic acids or not? And again, that's the major thing that you want to think is most of the H plus comes off, and that's all you need to kind of look at to calculate the pH. That wraps up part one